Hello, hello. Yep, I'll be starting up very shortly. Just gonna, wait a few minutes and let some people join in. Would hate to have a classroom and not get asked any questions, so I'd like at least for a few people to join before I start talking to a brick wall. So yeah, we'll be starting in just a few moments. Of course, I am active in the spaceflight Discord. You're stall 47. You've already been in contact with me. Ah, you're P23. Well, might I just say, congratulations on your 0649. You know what I mean? That is one of the best that I have ever seen. So, congrats on that. Your Delta X value was literally all balls. The Delta Y is more precise, so I think you had like, what, all balls on the Delta X and 4 balls 6 on the Delta Y. That is literally like the best I've ever seen anyone get. So, congrats on that. 95% luck, not gonna lie. Yeah. Well, what helps is a straight roll, a straight roller. I personally don't use it. I just sort of visualize it in my mind. For me, it's not a competition on the P23s. I just get a value that works and accept it. It's a competition on the P57, and that's a good one. But yeah, I think we're gonna get started. So I see that there are a decent amount of people in, so we're gonna get started right away. And I hope to keep these bootcamp videos under an hour. I'll try my best because I don't want it to be indigestible. Right? I don't want to have some like 4-hour stream that's super indigestible learning the spacecraft, like my power-up tutorials on the LEM, for example. Those types of videos have to be that long, unfortunately, but for bootcamp, we'll make it hopefully digestible. So we'll get started then, and I'm going to shut up my phone. So, well, thank you, thank you very much. I'm putting NASP on hold because there's a whole ton of new people that are joining reentry since Apollo 13 came out, and they're flying these spacecraft, and they're doing the things And then they get to Apollo and they hit a brick wall because all they've been doing is mindlessly following a checklist. They've never learned anything about how the spacecraft works, and they've never even, like, they don't even know what attitude 000 means, and they're flying Apollo. So we're gonna fix that, because sweet merciful Buddha, you should not be in the spacecraft unless you know what you're doing. So let's get on our business. So yeah, we are in the Mercury Redstone capsule, and here's what it sort of looks like. We'll go over the big things first. And unfortunately, there we go, in external view, you do need to be unpaused, but that's fine. So this big red tower at the top, we'll just sort of go top to bottom on the things we can see right now. This tower, this is called the escape tower, the launch escape tower. So at the very top here, we have the aerodynamic spike. It literally is just a spike to help with the aerodynamics of the rocket, because this escape tower is, well, as you can see, it's blunt-ended. It's not very aerodynamic. So the spike helps deflect the atmosphere, helps to cut through the atmosphere, so that we're not, ramming the blunt end of this escape tower into the air. Would be very terrible. Right underneath the aerodynamic spike, this is the fuel housed for the escape rocket. The escape rocket is a solid rocket booster. And to give you an idea on how much power these have, the escape rocket for the Apollo capsule, similar design, it has the acceleration of the Redstone rocket. So just to give you an idea on how exactly powerful these things are. You definitely don't want to be riding one unless absolutely necessary. So in this, there's a ton of solid fuel, and then there's another sort of segment, and a little tiny hollow tube down the middle. And that hollow tube down the middle houses a sort of gas cartridge, which we'll see later how that works. But the solid fuel burns, and it comes out these three little rocket nozzles, about the size of an Apollo RCS jet, to be honest. And that is how the spacecraft will yank itself away from the vehicle. Then this skinny little tube right here in the middle, you can see, this is, I forget the exact terminology, let me grab that. This is the pylon jettison rocket. So it's got that gas cartridge down the middle of this fuel canister. And this is sort of like a second rocket motor, but it fires cold gas, basically, and it's gonna pull the jettison pylon away. So this strut segment down to this attachment ring, that's called the retro pylon, or sorry, the escape pylon. And then the attachment ring here, it attaches to what is called the antenna fairing. Here's the antenna fairing. It houses a drag device, the drogue chute, and it also serves as the protection for, or it also houses antennas, and it serves as the protection for what's called the return package. Then we have the capsule here, which is comprised of the fore body right here and the aft body right here. And then we have our capsule adapter. And of course, the rocket. So these are the major components that we'll be taking a look at right now. Inside the rocket, let's start with over here. We've got some switches on the seat, and these are our battery tie circuit breakers, essentially. When you push it in, you tie that battery to its corresponding bus. So for this one, we tie the standby battery 1 to the standby bus. We tie standby battery 2 to the standby bus. Main battery 2 to the main bus. Main battery 1 to the main bus. Main battery 3 to the main bus. And the isolated battery to the isolated bus. So what do these buses do exactly? Well, we have a main and a standby. As you've probably guessed, the main bus functions as our main power source. The standby bus functions as a backup power source. That's probably really obvious, but what people don't realize is the function of this isolated bus. This isolated bus has a battery which carries additional voltage above the regular battery because it's going to be supplying a momentary burst of high amperage. And this happens anytime there is an explosive that needs to go off. So for anything down this row, except for retro attitude and retract scope, everything else has an explosive device attached. And this is responsible, or these are our single-use actions, and they're responsible for controlling the phase of the mission. The isolated battery is responsible for detonating those explosive devices. So that is the purpose of the isolated battery. However, it can also serve as a means to sort of grab tertiary power. So if for whatever reason we fail on main batteries 1, 2, and 3, and standby batteries 1 and 2, we can use the isolated battery, and we can tie it from the isolated bus, and we can tie it to the standby bus instead, and this will serve as a tertiary power source. You need to be very, very careful, because this will drain the isolated battery very rapidly. It's the only battery powering the entire spacecraft at that point, and you need it for all of these. You know, it's your lifeline. So definitely, if you get to the point of using the isolated battery as a tertiary power source, turn your power off when you don't need it again. So as you're drifting, turn your power off until your retro point, turn it back on, modify your retro values because that'll stop the clock from ticking. Well, I don't know about the sim, but in real life it would. And then do your retro at that point and go home. So be very careful with that. But it also serves as a tertiary power source. Now we'll go through left to right, and we'll take a look. So here we have the main fuse control panel. So how this works is it's a rocker fuse switch. So middle position is off, top position is the number 1 position, and bottom position is the number 2 position. So when you push it up, you make contact with a fuse, which is located in the switch. And for most switches, there are 2 fuses. So if one blows, you can switch it to the next fuse. And if the system continues to operate, then after you've switched it, there's no need for further diagnosis. If it doesn't operate after you've switched it, you've got a system problem. So 2 fuses to serve as redundancy. Does the backup battery get recharged? All batteries are charged before you switch to internal power. So we'll talk about that in a moment. These fuses, most of them have 2 sets of fuses. However, there are some which only have 1 fuse. So the main power control fuse panel, the ones listed for the number 2 position have direct contact solid conductors instead of fuses in the number 2 position. And this is because they are absolutely necessary for life. This, in the event of a malfunction, will ensure positive continuity until the equipment is no longer needed. Those equipment are, and I'll flip them into number 2 position, emergency capsule separation control, tower separation control, emergency retro sequence, emergency drogue deploy, emergency main deploy, emergency reserve deploy, emergency landing bag, and emergency rescue aids. In this position, all of these circuit breakers do not have a fuse. They are solid conductive material to ensure electrical continuity if a fuse blows. Because if one fuse blows and you switch it to the number 2 position, most likely it's some electrical fault of some kind and you'll blow the second fuse. This is minimum return capability right here. So let's talk about what each of these absolutely necessary lifelines are. Emergency capsule control will separate the capsule from the rocket. You can't re-enter with the rocket attached, you can't fire the retros with the rocket attached, or you'll blow yourself up. Emergency tower separation control, that's going to jettison the tower from the rocket. Again, you can't enter with a tower attached, or you're going to be having a bad day. Emergency retro sequence, this fuse has the logic for the retro rockets and the controlling of the timing and the attitude. Emergency drogue and emergency main, these deploy the drogue chute and the main chute, and emergency reserve deploy is a secondary fuse for the reserve deploy, which is a second main chute in the event that the primary chute is tangled up on deployment. So that's what each of these switches does. One thing to note, now that we've got our batteries in, we can turn the cabin lights on. Up next, right here, this panel, which is from here to the left, this is called the Control Mode and Systems panel. On this panel, we have the SQUIBS, which are those explosive devices we were talking about. We've got the auto retro jettison function switch. So if this is off, the retro pack cannot be jettisoned by the phase shifter, and this is the sequencer. The phase shifter controls the sequence. Bam, 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 bam. And then the programmer is what's going to write the sequence into its action. So the phase shifter over here will move to the next item. The programmer will take the signal for the item to begin and push it to the equipment, and then this entire panel is called the sequencer. So, yep, we've got the control mode and systems panel. So, SQUIBS, those are explosive devices. Auto retrojet prevents the jettison signal from being programmed into jettisoning the retro. Then we have the ASCS mode select. This is the automatic spacecraft control system. The three switches here, this one is called the ASCS mode. This one is called the RSCS mode, or the Rate Stabilization Control System mode. And this one is called the gyro mode. We'll talk about this when we get into orbit in a later video. Or, well, maybe we'll dig on it briefly in this video, but I'm not going to get into the nitty-gritty until we get into orbit. Here we have the decompress handle, which will vent the atmosphere from the capsule in the event of a fire. And we have the repress handle, which will pull oxygen from the O2 tank to repressurize the capsule after said fire has been put out. Next thing that sort of stands out is we have these four knobs: pitch, yaw, and roll, and manual. So we'll talk about these in a later video. So we're going to briefly touch on them here, but this is sort of the systems portion. And we'll talk about attitude control in a later portion. So we're going to do, first, we'll do systems, because everyone wants to see sort of what they're going to be operating first. Then we'll talk about theory, the theory of orbital mechanics. And then we're going to actually fly the spacecraft into an actual orbit. And so at the end of the theory video, we're going to do a launch. And the last bit of that launch will be sort of a homework question, if you will, about the principles of orbital mechanics and why the spacecraft will do what it does in terminal guidance. So, little spoiler for the ahead. And then video 3, we're actually going to be doing some maneuvering in orbit, and we'll talk about that. Attitude select. This changes the ASCS logic to hold a certain attitude, retro attitude, or reentry attitude. And we're going to talk about those again in a later video, but this essentially controls your main two attitudes you'll absolutely need to hold during the mission. Retro delay. On normal, this will fire the retros 20 seconds after the time to retrograde reaches 0. So once retro sequence starts, it will do its check for the retro attitude, and then it will add 20 seconds to the time. If this light goes green, adds 20 seconds, and fires the retro. In emergency situations, you may need to retrograde instantaneously. When you flip this to inst, and you turn on the retro sequence, the immediate second that the retro attitude light goes green, you fire the retros. Photo lights. This is just a light that's attached to the camera over here. Makes the console more visible. Cabin lights, you've got both off and left hand. TLM low frequency, this stands for telemetry, low frequency. So we've got low frequency telemetry, and we've got our high frequency telemetry. High frequency telemetry is actually on a circuit breaker, and low frequency telemetry is on a switch. Here we've got our rescue aids. This is a little antenna that'll pop up out of the that little part on the top called the recovery compartment, which has the main chute, the recovery, or the reserve chute. It has a little stick that'll come up. It has a dye canister and a blinking light. So that's the recovery aids. We've got auto, and then taking it to the right will manually deploy them. So keep this switch guarded. Or you've got auto, you've got manual. So keep the switch guarded. And right now it can't do anything because, well, all the circuit breakers are pulled. So coming up over here, we've got the abort light. This will signal you for an abort. An abort is performed by pressing Control, Shift, and Z all at the same time. We won't do that, of course. This is the pressure regulator. So when you're coming down for landing, you'll need to pull this so that water does not flood into the cabin. So pulling this will water seal the regulator so that the capsule doesn't flood and drown. Again, here are all our irrevocable actions, with exception to the retro attitude and retract scope. Jettison tower, jettisons the escape tower, separate capsule, jettisons us from the rocket. Retro sequence starts the checks and the firing of the retro and the jettison of the retro. Retro attitude, if you flip this to bypass, it means that the retro rockets can fire without this being green. So, as you know, as soon as this light turns green, it begins that 20-second countdown into firing the retro rockets. If this is on bypass, immediately when retro sequence comes on, it will start firing, or after those 20 seconds, it will fire the rockets regardless of if this light has ever been green. If you have it on bypass and inst, as soon as retro sequence starts, the retros will fire again, regardless of if this light has ever been green. Fire retro will manually fire the retros. Jet retro will manually detach the retro strap. Retract scope on auto will automatically retract the scope for reentry. Flipping it to manual means that you can toggle it with this lever here. 0.05G. This system changes the logic on the ASCS. And will start a small roll. It will start damping, pitch, and yaw to a better degree. And then it will also arm everything below it. Drogue is that drogue chute required to slow us down so that the main chute can open without tearing. The snorkel. This snorkel opens up fresh air into the cabin on entry. And then, of course, we've got our reserve chute. And the landing bag softens the impact with water, but mostly was added as a worry in case the capsule somehow landed on land. So we can see all these panels, all the white lights, or all the white have lights, and the black do not. So the black functions do not have indication. So that's something you'll have to keep in mind. So now we'll sort of go over, where is all of this stuff actually held? So we'll go over that because I'd like you to know what you're actually interacting with when you're interacting with it. So we will switch over. Here we are. So we can see right here, as I've said, we got the forebody, the aft body, recovery compartment, antenna fairing, and here we've got the recovery compartment. So we've got our ablative heat shield and our fiberglass attachment ring. Here is where the periscope is, as well as the umbilical door. So the umbilical will pop off of the rocket just before about like T-minus 30 seconds, T-minus 20 second mark. And that's why the periscope is open before launch. which is not simulated in reentry, but it would be in real life. You can look out the periscope before launch. The umbilical ejects, and then the periscope door closes automatically. Here's the window for observation. And this is the landing impact skirt. So this is the landing bag. It's airbag system. Poof, comes out, you know, same way that the airbag does, the old gunpowder and gas method. Here is the bulkhead. And this is the side hatch, which is explosively released in emergencies. So we'll go top to bottom then on this. So at the top, we've got jettison tower. And if we take a look, that jettison tower is going to activate the pylon jettison rocket, which is that tiny little spike down the middle here. Then we have separate capsule, and what that's going to do is it's going to fire off the explosive devices, and those will eject the clamps holding the capsule onto the rocket, and it will fire these three little motors, which are pretty much exactly the same as the ones on the rocket. You can see it's the same nozzle, except they're little tiny solid motors in here instead of one big one. Three little tiny ones, and these are called posigrades. These are posigrade engines. They'll boost the rocket, or they'll boost the capsule forward away from the rocket so that we can turn around without smacking into the rocket. Next up, we got the retro stuff. So we got retro sequence, retro attitude, retro fire, jettison retro. So we'll go over all of that. Retro sequence is the program, essentially. Retro attitude is determined by the gyros, and then retro fire. So these three things here, these are actually the solid motors, and you can see here we have the posigrade solid motors, and then we have the actual retro booster solid motors, three of them again, and these will fire us in the retrograde direction to return back to Earth. Notice that the posigrade and the retrograde engines are pointing in the same direction. We'll talk about that later. The jettison retros, again, uses those explosive devices to fire off the explosive here. Bam! The straps go this way, and the pack goes aft. There's also, in the middle, a little tiny explosive right in the center, which will just apply the slightest bit of thrust toward the heat shield. Not enough to cause any damage, but enough to give this pack a kick in the aft direction. So, little tiny circle, which boom, and give that thing a kick backwards. Next up, the retract scope, and we've already talked about that. 0.05G is a logistics thing. So we'll talk about the drogue and the main chute. The drogue chute is housed right here, you can see. And the attachment points for this are here, here, and here. And it's going to hold this entire capsule. It's a really small white parachute just to get us slow enough. Now when the main deploys, the little tiny rocket within the antenna fairing, again, gas generator rocket, not a solid motor, but gas generator. Explosives will fire on this ring. A guillotine explosive will fire and sever this cord. Actually, no, I lied. It will not. Explosive fires on the ring. Gas generator fires, kicking the drogue chute away. This cord pulls a mechanism which releases the main chute, and then that cord gets ripped off by the falling capsule, and the main chute comes clean. So the deployment, or the separation of the antenna fairing, is what deploys the main chute. The reserve chute has an independent deployment mechanism. Now we're on to the snorkel here. The snorkel is the device that helps you breathe as you're coming down. It equalizes the inside pressure with the outside pressure slowly as you come down. And then you're going to have an emergency O2 flow to keep that plus 5 psi from the outside in the cabin. So the snorkel will begin equalization, and then the oxygen will keep the structural integrity by adding 5 psi to the cabin plus the pressure as it comes down. So as you're falling, the capsule doesn't get crushed like a tin can. So the snorkel is very important. So you can imagine as you're falling, the pressure gets heavier and heavier and heavier. If you're only 5 psi, and that's it. You're dead. Oh, snorkel is an explosive, which will pop open a hole directly into the bulkhead and into the cabin, helps equalize the pressure, and then because you're equalizing the pressure as you come down, to maintain the 5 psi extra, you need to add higher pressure of oxygen into the cabin. And we'll talk about that procedure later. But that is... yeah, that's the anatomy of the spacecraft right there. So that completes that. We'll get to this later. Now we'll give our overview of the main panel. So the main panel is what's located here. And here. And okay, stream's back. Nice. I'm like, everything on my side is green, so it's got to be a YouTube problem. But here we've got the longitudinal acceleration that measures our g-forces. Right now we can see, even though we're not moving, we're reading 1g. Why are we reading 1g? Well, Earth's gravity. Here we have the control fuel for the auto tank and the manual tank. The auto tank has higher pressure RCS jets. So this is essentially our higher power RCS jets to control the attitude. But you can also, on the auto system, switch to the manual tank, and that'll go to those lower power RCS jets, low pressure ones. The manual tank will always use the lower power RCS jets. Here we have our rate of descent. And this is in tens of feet per second. And you'll see this sort of fluctuate up and down as you are orbiting. Here we have the barometric altimeter, measured in thousands of feet. Note the markings for the main chute, snorkel, and the drogue chute. Here we have a camera pointed at the astronaut, light test switch, our maneuver. Now this switch doesn't allow for, it doesn't make it allow for maneuvers, so this doesn't block off your RCS. What this actually does is it spins up the gyros in the gyroscope. These need to be spinning for 15 minutes prior to the use of the gyroscope. So that's what that maneuver switch does. Don't get that confused with the ability to maneuver. It's not at all what it is. Here we have the attitude indicator in roll, pitch, and yaw. So roll has 0 values, but up at the top is 0. Here we have 90, 270, and 180. Or, if you will, 0, 90, 180, minus 90, 0, if that's easier to think about it like that. Yaw is the same way, 0, 90, 180, 270, 0. So that automatically makes each large tick 30 and each small tick 10. So 10, 20, 30, 40, 50, 60, 70, 80, 90. And the exact same with the pitch. Notice retro marker on the pitch. We'll talk about that later, as well as talk about retro differences between reentry and real life, because at the moment there are some, but it will get smoothed out in the future. Here we have the RS, or the rate indicator. Notice the color of the needles. We've got a white, a yellow, and a pink. Notice white, yellow, and pink. This is our roll rate, our yaw rate, and our pitch rate. Each dot is 1 foot per second. So 0 in the middle, 1, 2, 3, 4, 5, 6 feet per second. 1, 2, 3, 4, 5, 6 feet per second. 1, 2, 3, 4, 5, 6 feet per second. Roll left, roll right, pitch up, pitch down, yaw left, yaw right. Then we have this sort of mechanical globe. The mechanical globe is called the Earth Path Indicator. And so you can set up your inclination, your polar, your orbit time, actually wind, and the orbit number. And this predicts where you're going to be landing if you fire your retros. Notice the accuracy confidence indication here. And that's position relative to Earth. And then in real life, believe it or not, there's actually supposed to be a little needle coming up right here. And that's going to show your landing area, basically. But it is not simulated in reentry properly. So the needle is not there. Here we have the satellite clock. This is our local time. Here we have the retrograde time. So this will begin counting down the minute the launch signal is received. The time for launch will begin counting up, and the time to retrograde will count down. So retrograde time is fixed, sorry. Time to launch counts up. Time to retrograde counts down as soon as we get the launch signal. And that's all controlled by this clock. We've got the telelight for 5 minutes to retrograde, and each of these counters, it's actually called a digidial. And then this is the retro time reset handle. In reentry, it's called the retro time modifier. In real life, this is called the retro time reset handle. We're able to add seconds or subtract seconds and minutes from our retrograde time, so we can modify that. Pulling the handle down will increase it, lifting it up. Sorry, pulling the handle down will increase, lifting it up will decrease. The time 0 button, in case this clock does not receive the launch signal and does not begin counting up, that time 0 button will activate that for you. There is a backup clock back here, which is not simulated in reentry. This needs to be manually wound using this handle, and at the 20-second mark, the handle needs to be pushed in, and that will activate this backup clock in case the primary one fails. It is important that everything happens in time because reentry doesn't really have a flight computer. Everything is time-based. Exactly like the Soyuz, it is all based on the time. So a backup clock is really important. Here, up in the white, we have our environmental controls. Cabin pressure. Notice it's atmospheric plus 5 psi. So held at 16 psi. We have the temperature of the cabin air in Fahrenheit. We have the temperature of the sensors in Fahrenheit. And we have the steam vent temperature. And different spacecraft call this different things. In Mercury, this is called a steam vent. In Gemini, you might see this as radiators. You might see this as boiler. In Apollo, you'll see it as the evaporator in Apollo. But all of it basically does one thing. You have a reservoir of water, and it flows through all the equipment, generating the heat. It gets really, really hot, and then it moves to the very outside of the spacecraft. And as soon as it touches the vacuum of space, bam, it evaporates immediately because water will instantly undergo a process called sublimation. In the lunar module, it is also called the sublimator, and this instantly evaporates the water. And what do you know about evaporating water? It's a higher energy state than condensed water. So what you're doing is you're immediately transferring all of that thermal energy from the water reservoir into steam and ejecting it out into space. And that process of instant evaporation by changing pressure is called sublimation. And this same reason is why ice immediately turns into gas, or can immediately turn into gas in space without going into liquid. It's also the same thing that happens to snow. If you have a gas lighter, you put it up to snow, it doesn't make a whole ton of water. It immediately goes into gas. And that is a process called sublimation. You're changing the boiling point by changing the pressure. And with the flame, you're changing the pressure through the heat. So this operates as our cooling system. Then we have our suit environment. We've got our cabin O2, so this is the partial pressure of oxygen. And then we have our actual oxygen tank quantity. We have the primary tank and the secondary tank. The primary tank is held at a slightly higher PSI than the secondary tank, so that when the primary tank depletes, it will automatically grab from the secondary tank. Now these tanks, they are they're sort of held at, I can't remember the exact number, so let me get it for you. Yeah, these tanks are held at 7,500 psi, roughly, of gaseous oxygen, 100% pure. We've got the suit fan switch, so normal operates both number 1 on number 1 only, and number 2 on number 2 only. Cabin fan is for the cabin fan. These fans help to sort of remove odor, remove moisture from the air, so that's why we've got our excess H2O and excess H2O for suit and cabin. So what this system is responsible for is essentially keeping the pressure of the cabin and the suit independently. These are independent systems. It removes odors, it scrubs CO2, and it removes moisture, as well as maintaining temperature and pressure. And we have enough oxygen and coolant for 20 orbits, which is well above the orbit decay rate. So this capsule can stay alive for 20 orbits, but it can physically only stay in orbit for about 7 orbits. So a lot of redundancy. And if you need emergency flow on the O2 for higher pressure oxygen, you can do it and not have to worry about your quantities here, not have to worry about stretching thin. You have plenty of depress and repress capabilities without stretching thin the amount of orbits you can stay out for. Over here in the yellow, we have the EPS, or the electrical power system. We've got DC volts over here, and we've got DC amps over here. So this is called a voltmeter, and this is called an ammeter. The ASCS AC bus, this runs off of AC power. We can tie that to a standby bus or the normal main bus. So we've got the we got the normal ASCS bus, and we've got the standby ASCS bus. Standby bus can automatically be engaged as well if the normal bus fails. We've got that telelight to indicate if our normal bus has failed, and the standby AC has automatically kicked in. We can bypass the ammeter, so that will power up the systems further down the line. Power off will completely turn the whole capsule power off. Not right now because we're on a ground power supply, and the normal will have this meter go. So if you have a fault with this meter, you can maintain spacecraft power without the risk of fire by just bypassing the meter. And then here is our AC voltmeter. We've got our battery ties, so standby batteries, we can click them on to the standby bus, and we can tie the isolated battery to the standby bus as well. Inlet valve power, so this is our ground support equipment. By taking this to bypass, you would theoretically bypass the ground power and go momentarily internal, not simulated in reentry. Audio bus, we've got 2 buses for audio. We've got the normal and the emergency audio bus. Here we can measure our 250 volt amp bus, 150 volts and amp bus, ASCS bus, standby bus, and the cabin fans. Cabin fans run on AC. Fans run on AC because they need a spin. So they will have equipment normally in them, the motors, to convert DC into AC to keep that spinning motion going. main monitors the main DC bus. So a lot of equipment runs on DC, some of it runs on AC. DC's direct current, flat line, stays at 0 volt, stays at the nominal volts. So you essentially remove the AC component, and it's flat. It does not increase in volt and decrease in volt momentarily. It is just pure volts at that steady number. To get AC, we have an equipment called an AC inverter. And actually, we can control the temperature for said inverter here. And this will use a signal generator. This will use a sine generator to create that rising and falling edge and alternating that voltage up and down, making AC current. Here we've got our annunciators. When the switch is to the right, we can get alarm tones for the annunciators, and when it's to the left, we've acknowledged the annunciator. The alarm will go and turn off, but the light will remain on. And here, we've got our further circuit breakers for our soup fan, our inverter control, this guy here, our retro jettison, our manual retro fire, the programmer, which remember, the phase shifter controls when the next event starts, and the programmer pushes that next event signal into that piece of equipment it operates. And of course, the blood pressure tester here. Here we've got Vox power. So that stands for voice operated transmission power. We can go record on the tape only, or we can go transmit and record. And then we also have the communication key, which is essentially push to talk button. Here we have the UHF delayed function. It's either on norm or RT for receive transmit. Or sorry, RT for real time or norm for delayed time. My bad. And then UHF, we've got a low power and high power UHF system. We can go transmitting on high frequency or ultra high frequency. And we have the beacon, which is essentially the equivalent of an airplane transponder. We have it on ground command or continuous. Over here is the ECS controls. Again, pulling that out gets our high pressure flow. And we can see that really is pumping oxygen in. And here's what the alarm sounds like. And then these control the temperatures. So you can see, as we get the temperatures up, and for dramatic effect, let's get it all the way. And we can really see, in space we would, these values would begin to drop really, really fast. But because we're not in space, the steam vent, which remember is the process of sublimation, can't take place because there is no pressure differential. Sublimation relies on the pressure difference to instantly turn water or ice into steam. So we can't cool the spacecraft down. There is no way to reject the heat of the spacecraft without that big pressure difference. Curiously, though, I'm interested to see if we do turn all of the circuit breakers on, if we'll actually get that temperature coming down, or if that is simulated properly. And it looks like it is indeed simulated properly. Good. So that's sort of the spacecraft systems. Any questions? What are we at time-wise? Over an hour. Unfortunate. I wanted it to be under an hour, but that's okay. Any questions? Have I done a good job explaining everything? Did I go too fast? We'll take a deeper dive into the system when we get to the last lesson of this course, which is emergency situations. Then we'll really take a deep dive into these systems, and that's probably going to be split into several parts of maybe 10 or 15 minutes, talking about the failure situations that can occur on each system and what to do about them. Yeah, you are a bit late. We are actually just going to wrap up. I may stream again tonight, but I'm only streaming for a break from homework, to be honest. And I'm starting the Astronaut Bootcamp. So that, you know, people flying this capsule, they know exactly what they're doing. And they're not just blindly following a checklist. Oh yeah, one thing I forgot to mention, the periscope. We'll talk about this when we're in orbit. But yeah, other than that, that's pretty much everything. So I say, as a little reward for sitting through an hour of just purely talking about engineering and the system, the physics of the systems themselves, let's actually see a launch. And I'm going to perform the launch, but I will not really be talking about what's going on, because we'll save that for orbital mechanics theory in the next video. So we'll get this thing up just as a little reward for all of your listening. It's not every day you get to sit through an hour of process engineering. We will be covering more on what each of these circuit breakers does in our emergency systems, or emergency operations, but based on the name, it is pretty self-explanatory. So, but we'll talk more about what they do in the actual emergency situations. In. We're going to have to push through these checklists pretty fast, because we talked for an hour. We've only got 30 minutes left to do all of this. Good. 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 Here, check this out. Ah, it's right here. Yeah, there we go. And also check this out. See that? Nice functionality. There we go. Yeah. Okay, there we go. I switched from the 5 gigahertz band to that 2 gigahertz. There's ranging problems with the router, so if you're ever having signal issues and you're on the 5G, switch to 2G, because it has much, much higher range. The lower the frequency of a signal, the further it can go before it undergoes signal degradation. So if you ever have Wi-Fi problems, switch to that lower hertz. And we're back up. Audio bus is norm. Let's get that back to pins. Under 15 volts. Yep, it's good. Box is off. UHF delayed function, so we are on delayed time. Transmit off. Beacon ground command. All warning lights to tone. I call them enunciators. Checklist calls them warning lights. Same thing. To mark, to mark, to mark. Maneuver switch on. We did that earlier. Abort capability test. So we will take the ammeter to norm. And we will select SQUIBS to arm. And monitor isolated bus. And when we get to that abort test, we can see rise in the amps, and the abort light comes on. And that simulates firing of the explosive systems to jettison. So the isolated battery, as you know, controls all those explosives, the sequencing of the rocket and everything. So anytime we stage, the isolated battery will jump up for most things. Now we can start the abbreviated interior check. SQUIBS switch arm, auto retrojet arm, auto. Rescue switch auto, retro delay normal, pressure regulator in, retro attitude auto, retract scope auto, landing bag auto, control fuel 101 and 101%. We would write down the values of these gauges. Suit fan norm, cabin fan norm, DC volts select main, ammeter norm, ASCS AC bus norm, standby battery on, isolated battery tied to standby bus, inlet valve power normal, audio bus switch normal, fans AC bus switch normal, Vox power off, delayed function normal, UHF select high power, UHF transmit off, and beacon switch to continuous, and emergency O2 handle in. Now we can start full internal power at the T-minus 10 minute mark, so we'll time skip down to T-minus 10, and we'll go for full internal power. Bam! We got the rise in our amps now. So we're operating on vehicle power. Click through, monitor everything has amps going. That's good. Now we can take isolated battery off the standby bus and the standby bus off the main bus. So there we go. Nominal volts and amps. We'll click through again. We can see these three batteries will have 0 amps because they are not in use. And now we can start final checks at T-minus 5 minutes. Launch control ready. Transmit on UHF. Mark, mark, mark. Time 0 cover remove. Monitor battery 1. SQUIBS switch arm, auto retrojet arm, and we're ready. We'll talk about why we're monitoring battery 1 in our emergency situations video. So now we'll get launching.
9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, lift off and the clock has started. On your way. Yes, sir. Reading you loud and clear. I tell you.
We see that moon, and that's where we're gonna be going.
Cabin pressure is holding at 5.5. Cabin holding at 5.5. I understand. Cabin holding at 5.5.
Yep. So, when we get up high enough, there are some valves in the bulkhead which are opened so that we drop down and we maintain that 5 psi differential. And as soon as we hit 5 psi cabin pressure, those valves will shut closed, and then we'll maintain that 5 psi difference between space and the capsule. Because the capsule derives its structural integrity from its internal pressure, exactly like a soda can.
Cut off. Tower jettison green. All right, sure now. Green.
Okay, we got the turnaround. While we're up here, we'll just test out manual control here. Exactly as they did in real life. Notice how you build up rates a lot faster on the fly-by-wire, because fly-by-wire draws from that higher power auto tank. So notice how we are able to pitch up and pitch down and basically stay at the same attitude as when we began that maneuver compared to manual control, which would cause significant deviation compared to that auto tank. Notice how the gauges respond when I move the temperature, now that we're up in space and we can undergo the process of sublimation. Retro sequence start. Retro attitude is green. Retro warning light is on. Retro fire. This flight is suborbital, so we didn't need to fire the retros. However, it's a great test before we go orbital to make sure that it still works. Retro is the lifeline, so it's a great test. Notice the roll that started when we got that 0.05G entry interface light. Yeah, that's because I think that the retro reticle and the retro indicator are actually for the Redstone suborbital flight. That's my theory anyways. So, because, like, think about it. If you're pointed all the way down here in your orbital flight, you would be pointed down. You wouldn't be pointed perfectly retrograde, so just a theory of mine. And it's something I'll have to test. It's very, very new, so I always retro at 000 in orbital flight. Notice RCS is all burning right now. We are starting the peroxide dump process, basically. So this is pretty normal, and it will stop. The peroxide will dump, and then the cold helium will dump, and you'll see the RCS indication fall immediately to 0. And notice the digidial counting. And that drogue chute immediately opens. RCS cuts off. And look at that. And there you go. Peroxide is dumped. Landing bags out. And that successfully completes the suborbital flight. So, stay tuned for more, and thanks for joining. Just a few things left we gotta do now. Water seal the pressure regulator. Go to real time on the UHF DF function. And that's it. Until splashdown, but that's going to take like 5 minutes. And I'm sure none of us want to stay here watching this for 5 additional minutes. We'll do it in our re-entry part of this tutorial. So here, we'll cut it off here until part 2 of Astronaut Bootcamp. Thanks for tuning in. I hope this provides some insight as to how this vehicle works, a little bit about the operations, and we're going to learn a lot more about these systems in depth and their operations when we get to the emergency procedures part. Well, round 2 is going to be very theory heavy, so hope you're in for it. Because definitely people are going into this not understanding what an apoapsis and a periapsis is, what a parasynthion is, perigee, apogee, ascending node, descending node, you know, what prograde, retrogrades, normal in, normal out, radial in, and radial out are. They don't understand how exactly an orbit works, and they don't understand that when they make a maneuver for everything except for radial in and radial out, you affect the opposite side of your orbit, not the side of your orbit that you're actually on. And so these are things that are very hard for people to grasp. And so it's going to be very theory heavy on round 2. So, a few homework questions. Don't answer them. Answer them in the comments after the stream ends. We don't want people to just look and see the answers. But we've got... Which bus? All right, those are your 4 homework questions, if you feel like doing them. 1, which bus powers the explosive devices? or SQUIBS? 2, what are those SQUIBS used for? 3, which circuit breakers do not have a secondary fuse? And 4, what is the stack of lights called? And actually, we'll do 5. Stack of lights on the left over here. And number 5, why do some circuit breakers not have a secondary fuse? That's a good one. Those are your 5 questions. Thanks for watching.